Okay, some more problems from section 6.2, and this is number 59. And we have the integral from 0 to 1 of the square root of t to the 5th plus 2t times the expression 5t to the 4th plus 2 dt. And if I look in the inside of this, the derivative of that's just going to be 5t to the 4th plus 2, so it's right there. So it looks like I'm going to work for u to the n du. So first of all, I'll write this in exponential form. So that's t to the 5th plus 2t to the 1/2 times its derivative. So I'm going to let this be u. So let t to the 5th plus 2t equal u. So this would be u to the 1/2 times this again 5t to the 4th plus 2 dt. And I've got to get this in terms of u. So first of all, I'll take the derivative of this, which is going to be 5t to the 4th plus 2 dt. It looks like I've got a match right there. So that's matched up, so this becomes du. So I'm in real good shape. I just have to find my values at u. So u at 0, if I evaluate u at 0, I get 0. And then if I evaluate u at 1, u of 1, I get 1 to the 5th, which is just 1 plus 2 times 1, which is 2, so I get 3. So there I'm all set, ready to go. Now this is a lot simpler. See how much simpler this is than this. So it's nice to leave it in terms of u. So if I take the antiderivative, I add 1, I get 3/2. Okay, u divided by 3/2 or times 2/3. And I'm going to evaluate that from 0 to 3, so I use the second part of the fundamentals of calculus, f of b minus f of a. Here's my f of b. I'm going to take 2/3 and I'm going to put 3 to the 3/2 minus 2/3, 0 to the 3/2. Now that's just going to zero out, so I just have this term. How do I evaluate this? Well, the square root of 3 is a little bit, and then cubing the square root of 3 doesn't, you can do it like this, but I like to, in this case, get a little bit bigger first, then take the square root. So 3 cubed is 27, so this is the square root of 27, and this is 2/3. And the square root of 27 is the same thing as 9 times 3. The square root of 9 is 3, so that's 3 times the square root of 3 times 2/3. These 3's cancel, so I end up with 2 over this. 2 times the square root of 3. That's fine. Or you can simplify it. Sometimes they simplify these in decimal numbers. You can just check that. Make sure you get the same thing. Okay, 61. Here's 61. Okay, so we have the integral from 0 to 7 of dx over x plus 2. And remember, when we have a fraction, we always look for 1 over u du. And it looks like we've got this. In other words, I can write this as 1 over x plus 2 dx. And the derivative of this is real easy. It's just 1 dx, so I've got it. All right. So I'll let u equal x plus 2, so I've got 1 over u dx. But if I take the derivative, du equals dx, so it just fits right in. Now I've got to figure out what my variables are going to be. So my u is x plus 2, so 0 plus 2 is 2. And 7 plus 2 is 9, so I'm integrating from 2 to 9. 1 over u du. And the antiderivative of 1 over u du is just the natural log of the absolute value of u. So I use the second fundamental theorem of calculus, or the second part of the fundamental theorem of calculus, f of b minus f of a. So f is the natural log. And the absolute value of 9 is 9, so I don't need the absolute value anymore, so it's just the natural log of 9 minus the natural log of 2. And that's the same thing as the natural log of 9 over 2. And then I think they have a decimal answer. You can work that out on your calculator. You should get what they have. Okay? All right, let's try 63. Okay, here's 63. And we have the integral from 1 to 2 of dt over t minus 3. And this is the same thing, 1 to 2 of 1 over t minus 3 dt. And I'm going to use this 1 over u du again. So I'll let u be t minus 3, so du with dt. So I've got 1 over u dt, but that's all just a 1 over u du. I just have to change the limits. So u is t minus 3, so u of 1 would be 1 minus 3 or negative 2. And then u of 2 would be 2 minus 3 or negative 1. So I'm going from negative 2 to negative 1 of 1 over u du. And again, that's the natural log of the absolute value. So when I evaluate that f of b minus f of a, if I put negative 1 here, the absolute value of negative 1 is just positive 1. So again, I have the natural log of 1 minus the natural log of -2, the absolute value of -2, which is just the natural log of 2. And that's the same thing as the natural log of 1 divided by 2. And again, they have a numerical answer. You could just simplify that. Or you just worked out in your put that in your calculator. You won't have any trouble. And the last one here, number 65. This is the last of the set, I believe. Bring this up just a little bit more. There we go. Okay. The integral from -3 to -1 to 3 of x over x squared plus 1 dx. And again, we want to look at the bottom. What's the derivative of x squared? 2x. So I've got the x there, so I can try to get another 1 over u du. So I'll rewrite this so it looks a little bit more like that form. 1 over x squared plus 1 times x dx. So I'll let u equal 1 over, I'll let u equal x plus 1. So I've got 1 over u x dx. So I've got to get this in terms of u, so I'll take the derivative of this. So the du, the derivative of u is du, the derivative of this is 2x dx. And I've almost got a match. I just have to move the 2, so I divide both sides by 2. And here's my x dx that matches that. So instead of writing x dx, I can write du over 2. I also have to change my limits, and u equals x squared plus 1. So -1 squared plus 1 is just 1 plus 1 is 2. And 3 squared plus 1 is 9 plus 1 is 10. So those are my new limits. I can take the 2 in the bottom and put it in the front, and here's what I have. 1/2 the integral from 2 to 10 of 1 over u du. And then that's going to be the antiderivative of that will be the natural log of u, going from 2 to 10, using the f of b minus f of a form, fundamental theorem of calculus. So I got 1/2, and this is my natural log of 10. The absolute value of 10 is just 10, divided by, or minus, the natural log of 2. That's my f of b minus f of a. And that's the same thing as 1/2 the natural log of 10 divided by 2. Remember, the difference of the logs is the log of the quotient, but 2 goes into 10 5 times, so that's just 1/2 the natural log of 5. And then if you look that up on your calculator, you'll find the answer they have in the book matches that. Okay? Hope those help.